Congratulations, you've made it to the second video. So, the first thing we have to do when seeing if our mechanism is right is one thing we can do to support our mechanism. First of all, is that the mechanism has to add up to the overall reaction. And backing up to page 38, if you add these two reactions up, the NO2s, one of them anyway, cancels out. The NO3, the intermediate, must cancel out, which leaves, back to page 37, the overall original reaction. So that's all fine. I mean, you can construct any mechanism you want that adds up to those reactions. That's not really all that impressive. So fine, at least that's taken care of. Page 40 solves half the problem. What about the other half? So a multi-step mechanism is always going to have one step that is much slower than all the others. That one is called either the rate determining or the rate limiting step. Either one, rate determining step, rate limiting step, because it's the slowest step in the process, and it causes the it sets the rate. I've used this example before. One section's heard it, one section hasn't. Imagine you're driving. Oh, I know which one. It's Joe Christian, who said that he doesn't care about the 55-mile-an-hour speed limit in Northern State. He's going 80, but whatever. Okay, I don't want to ignore that and say that if you're going 55 down the Northern State Parkway, but Aunt Bertha and Uncle Fred are up there in two separate cars in the right lane and the left lane going 30, how fast can you go? And no, Joe, don't go on the grass median or on the side, but you can only go 30 because the slowest step in the process is going at 30 miles an hour. So how can you relate that to the activation energy of the slowest step? If it's the slowest step in the process, what do you think as far as its activation energy is concerned? What do you think? And then once you decide that, I want you to try and think a little outside the box and draw a potential energy diagram with your groups of a multi-step reaction. This is kind of an aside. I'm actually not going to put the answer up right now. I'll do it when I get back. These two things really aren't necessary for what we're about to do. So try that now. You can press pause and give yourselves a minute and a half to do that. Okay, back to the mechanism. So here's the extra information. As I said, one of the steps is going to be much slower than the others. And so here we are halfway down page 40. And I've rewritten the mechanism. And I've let you know that the slow step is this first step, where the two NO2s collide to make the NO3 and a molecule of NO. So if that's the slow step, then that's the one that you're going to use in order to figure out the rate law. So you pay attention to that slow step, and from what you know of elementary steps, write down the rate law that you would expect. All right, press pause and do that. Okay, so here's what you would do. If indeed you see a couple of NO2 molecules, and they are the reactants in the slow step, you ignore the fast step, and you just write the rate law. Rate equals K NO2, NO2, there are two of them, so squared. So, and if you look back to page 37, it's exactly what I told you the rate law was. And mine's not filled out anymore because I quit out of the program in between, but you wrote K times NO2 squared. Now that's exactly right. Does that mean that the mechanism is correct? Raise your hand if you think yes. Raise your hand if you think no. Well, you're both wrong, because the answer is we just don't know. It's possible that the mechanism is correct. All we can say, though, is that this mechanism is supported by the rate law. But we can't say that it's absolutely correct. We can say that the rate law agrees with this mechanism, or that this mechanism agrees with the observed rate law, either way. But you can't really prove that it's true. You can prove that it's not true. You can prove a mechanism false. Okay, so if you're given a mechanism that didn't agree with this, then you could say that must not be the mechanism. But you can't prove that it is the mechanism, because you could imagine you could draw other sets of steps that would also give an NO2 squared that might not look exactly like this. So that's possible. So it's one of the unfortunate little pieces. Now, I want everybody out loud in unison with the proper caps to say this next sentence, a very important sentence here at the bottom of page 40 with the 3 asterisks on either side. Okay? And go. Yeah. Okay, now I want to show you exactly what I mean by this. And in order to do that, I'm actually going to take the same example that we have, but I'm just going to cut and paste it onto a different page. And you should work on a separate sheet, or if you have some room over here on the right side, you can do that. But the reason I'm going to do it is I'm going to switch the slow and the fast steps. So what if this were the fast step and this were the slow step? I want you and your groups to take a second, or 30 seconds, whatever, press pause, and write the rate law that would have resulted. Okay. If you did it properly, you should have come up with this. There is an inherent problem with this rate law, and that is the presence of NO3. The issue is that the overall reaction, and I'm just going to go copy and paste it right now from page 37. You'll notice that this reaction doesn't have NO3 in it. So if you were to write a rate law, it has to be in terms of the overall reactants. So now I've got a problem. I have NO3 in there, and I just told you, and you just said in some sort of weird trance that NO3, the intermediate, can't be in the rate law. So what do? Well, you can't just get rid of it, because it does depend on NO3 if this were the slow step. But what you have to do is you must go substitute for it. You have to go back and figure out, well, where was this NO3 from? And for that, you end up having to go back to the fast step. And you go say, oh, that NO3, that one was made from a couple of NO2s. So you go ahead and substitute. What you end up doing is so the CO stays there, okay? I'll put it back there in a second. But the NO3 gets substituted. Instead of NO3, there were a couple of NO2s that made the NO3. And so you substitute. Right? You substitute. You don't delete. You substitute the intermediate for things that are in the overall reactants, just like that. And that's going to be important as you go ahead and finish up the other worksheets. And you'll see from the plans that I've left what problems you can and should do at this point. Okay? So there you go. That's the whole thing on mechanism. You saw the two parts. It has to add up to the overall reaction. It has to agree with the rate law. That doesn't mean that it's definitely correct. But you certainly, if it's not correct, you can say that that must not be the mechanism. And the added piece here is that this presence of an intermediate in a rate law must be substituted for. Now, just as a quick little finish up, if I were to have proposed this mechanism, you could have told me clearly that this must not be the correct mechanism for the reaction, because I told you initially that the rate law was just KNO2 squared. The presence of the CO here means that it must be wrong because it doesn't agree with the rate law. And so that would have told you that this mechanism was wrong. But be that as it may, this was mainly as an exercise so that you could see what happens when an intermediate is in your rate law. All right, good luck the rest of the way.